Hey everyone, welcome back to the channel. In this series, we built a complete machine learning weather forecasting system from scratch using Python. After part 1 and part 2, I received a lot of feedback through comments and emails. Many of you asked for improvements, advanced features, and a more production-ready version of the project. So in this video, I'm presenting the final and enhanced version of this entire system. This isn't just another part. It's the upgraded version of everything we built before. We're refining the architecture, improving performance, organizing the project in a cleaner way, and adding features that make it feel like a real-world AI product. The goal is simple: to turn this into something you can confidently showcase in your portfolio, submit as a final year project, or talk about in interviews. We're taking everything one step further, making it cleaner, stronger, and more professional. So make sure you watch till the end. Let's get started. Now, before we start building the advanced system, let's quickly set up everything we need. Make sure you have Python and Visual Studio Code installed on your system. Also, make sure you are using Python version 3.10 or higher. For live weather data, we'll use the Open Weather Map API, and you'll need a free API key from their website. For historical data and forecasting, we'll use the Open Meteor API, which is completely free and doesn't require any API key. Now let's move into VS Code and set up our project. First, create a new folder. I'll name it Advanced Weather V2. Now open this folder in VS Code. Next, open the terminal and create a virtual environment. Once it's created, activate it. Now install the required libraries. We're using Pandas and NumPy for data manipulation, scikit-learn for our machine learning model, joblib inside Django for caching our model to save time, and FileLock to make sure our training happens safely in the background. Once installed, let's create our Django project. Type Django-admin start project weather project. Don't forget the dot at the end, which creates the project in the current directory. Next, let's create the app that will hold our powerful forecasting engine. Type python manage.py startapp forecast. Now we need to tell Django about our new app. Open the settings.py file inside the weather project folder. Scroll down to the installed_apps section and add forecast to the list like this. Save the file. Also, while we are talking about settings, Django automatically checks inside your app folders for a folder named static to serve your CSS and JavaScript. So we don't need to write any extra configuration for static files inside settings.py. The native static_URL equals "static" / configuration at the bottom is already enough. Before we write our logic, let's configure the URLs. First, open urls.py inside the weather project folder. We need to import the include function from Django.urls. This allows us to reference the URLs of our app. Then, inside the URL patterns list, type path include forecast.urls. This routes traffic hitting the root URL to our forecast API. Now, inside our forecast folder, create a new file named urls.py. Open it and import path from Django.urls and views from the current directory. Right. From Django.urls, import path from .import views. Then define the URL patterns list and add path hash views.weather underscore view name weather underscore view. This links our empty root URL directly to the weather underscore view function we are about to create. Now, the most exciting part, open the views.py file inside your forecast directory. This is where we write the entire brain of our AI. First, we need to import all of our powerful tools. We import rendering from Django, requests for our API calls, pandas, and NumPy for handling our data arrays, and, critically, time series split and HistGradientBoostingClassifier from Sklern. We also import date time, time delta, and time zone because handling time strictly in UTC and converting to local time is vital for accurate weather tracking. Next, we define our open weather map underscore API underscore key. As a best practice for production, we use os.getEnv to grab it from the system environment, but we provide a fallback string so it works out of the box for testing. Before we start writing our core logic, we first set up some important configurations. Now, before we go deeper, I just want to mention, since this project has a lot of detailed code, I won't be writing everything from scratch here. Instead, I'll walk you through the code and explain how everything works, so you can understand the logic clearly without wasting time. Here, we are optionally importing FileLock, which helps us ensure thread safety. This is useful when multiple processes try to access or write the model file at the same time. It prevents conflicts and keeps everything stable. Next, we define our API configuration. We store the Open Weather Map API key using environment variables for better security, and we also provide a fallback value for development. We also define the base URL for the API so we don't have to repeat it multiple times in our code. Finally, we create a dedicated directory to store our trained machine learning models. If the folder doesn't exist, it is automatically created. This helps us cache models and reuse them instead of training again and again. Now let's look at our first core function, fetching the current weather data. This function connects to the Open Weather Map API and retrieves real-time weather information for a given city. We build a request URL using the city name, API key, and specify metric units so the temperature is returned in Celsius. Then we send a request to the API and convert the response into JSON format. We also include error handling. If the city is not found, the system raises an exception. This makes our application more robust. Now, one of the most important parts here is time handling. The API returns timestamps in UTC, so we convert sunrise and sunset times into the city's local time zone using the time zone offset. This allows us to accurately calculate things like daylight duration, which adds more realism to our application. Finally, we extract all the important weather features like temperature, humidity, pressure, wind speed, cloud coverage, and geographic coordinates. All this data is then returned as a structured dictionary, which we later use in our machine learning pipeline and front-end UI. Now, this is where our system becomes truly intelligent. Instead of only fetching future predictions, we use the Open Meteor API to get both past data and future forecasts together. Here, we pass the latitude and longitude and request multiple weather features like temperature, humidity, pressure, precipitation, and wind data. But the most important part is this parameter, past_days equals 1. This allows us to fetch real data from the last 24 hours. And this is extremely powerful. Because machine learning models don't just need current values, they need trends. For example, if pressure has been dropping over the last few hours, it can indicate incoming rain. So instead of guessing trends, we use actual historical data. We also request forecast data for the next couple of days so we have a complete timeline. Once we receive the data, we convert it into a pandas data frame. This makes it much easier to process and analyze. Then we align the data with the current time, so we can accurately locate where we are in the timeline. Finally, we return the dataset along with the current index position, which will later help us extract features for prediction. This is the key difference between a basic weather app and an AI-powered system. We don't just look at the present, We learn from the past. Now, to properly train our machine learning model, we need a strong historical dataset. So instead of using a static file, we dynamically fetch real-world historical data using the Open Media Archive API. Here, we request around 365 days of hourly weather data. This includes temperature, humidity, pressure, precipitation, wind, and cloud cover. The reason we use one full year of data is to capture seasonality. Weather patterns change across seasons, so the model needs to see examples from summer, winter, and rainy periods to learn properly. Once we receive the data, we convert it into a pandas data frame and organize it by time. Then we clean the data. We resample it to ensure consistent hourly intervals, and we handle missing values using forward fill. This ensures the dataset is continuous and reliable. Finally, we end up with a clean dataset of around 8,000 plus rows, which is ideal for training a robust machine learning model. This step is critical because the quality of your model depends directly on the quality of your data. Now, this is the most important part of our entire machine learning pipeline: feature engineering. This is where we transform raw weather data into meaningful patterns that the model can understand. First, we create our target variable, whether it will rain in the next 6 hours. So instead of predicting the present, our model is actually learning to predict the future. Next, we create time-based features like hour of the day and day of the year. We also convert them into cyclic features using sine and cosine functions, so the model understands patterns like daily and seasonal cycles. Then we create lag features, which means we look at past values. For example, temperature or pressure from 1 hour ago, 3 hours ago, and 6 hours ago. This allows the model to understand how weather is changing over time. We also calculate changes like how much the temperature or pressure has increased or decreased. This is extremely important because sudden drops in pressure often indicate incoming rain. We also create rolling statistics like averages and totals over the last few hours. This helps the model capture short-term trends. Finally, we create special indicators like whether it rained recently and whether pressure is falling or rising. These are strong signals that help the model make better predictions. At the end, we remove any missing values to ensure clean data. This step is where raw data becomes intelligence, and it has the biggest impact on model performance. This is similar to how humans predict weather. We don't just look at the current temperature, we think about how it has been changing. Now that we have created all our features, the next step is to prepare the data for training. Here, we define a list of feature columns. These are the inputs our model will use to learn patterns. This includes current weather conditions, time-based features, and most importantly, historical and trend-based features. Then, we separate our data into two parts. X contains all the input features and Y contains the target variable, which is whether it will rain in the next 6 hours. This step is important because machine learning models require a clear separation between inputs and outputs before training. This is the final step before training, where we convert our dataset into a format the model can actually learn from. Now we move to the model training step, where our system actually learns how to predict rain. Here we use a machine learning model called HistGradientBoostingClassifier. This model is fast, efficient, and can handle missing values very well, which makes it suitable for real-world data. Another important thing we handle here is class imbalance. In weather data, rain doesn't happen all the time, so the dataset is usually imbalanced. To solve this, we use class weighting, so the model doesn't become biased toward predicting no rain. We also evaluate the model using F1 score instead of just accuracy. This is important because F1 score gives a better measure when dealing with imbalanced data. Next, instead of randomly splitting the data, we use time series split. This ensures the model is trained on past data and tested on future data, just like real-world conditions. After validation, we train the model on the full dataset. Finally, we return the trained model along with performance metrics. This makes our model more realistic because it learns patterns over time instead of random data splits. This is like training a student using past exam papers and then testing them on future exams. Now, training a machine learning model can take time, and we don't want to retrain it every time a user makes a request. So here, we implement a smart caching system. First, we create a unique key based on the location, using latitude and longitude. This allows us to store a separate model for each location. Then we check if a trained model already exists on disk. If the model is less than 24 hours old, we simply load it instead of training again. This makes our application much faster and more efficient. But if the model doesn't exist or is outdated, we train a new one using our full pipeline, fetching historical data, engineering features, and training the model. We then save this trained model using joblib so it can be reused later. We also use file locking to ensure that if multiple requests come at the same time, only one process trains the model while others wait. This prevents duplicate work and avoids file corruption. This is what makes the system production ready, optimizing both performance and reliability. This is like saving your work instead of redoing it every time. Now this is where everything comes together, making the actual prediction. In this function, we use our trained model along with real-time data and recent historical data to predict the probability of rain. First, we make sure we have enough recent data available. If not, we return a fallback prediction. Then, instead of using any guessed values, we extract real historical values from the dataset, like temperature, humidity, and pressure from the past few hours. This is very important because our model relies on trends, not just current values. So we calculate changes like how pressure or temperature has evolved over time. We also compute rolling averages and recent rain indicators, all based on real data. Once we have all these features, we build a feature vector that matches the exact format used during training. Then we pass this data into our trained model. The model returns a probability score, which represents the likelihood of rain. And that's what powers our AI prediction system. This is the final step where data, features, and the trained model come together to produce an intelligent prediction. This is like giving the model the current situation along with recent history and asking, based on what you learned, what will happen next? Here we have a small helper function that converts wind direction from degrees into a readable compass format like north, south, or east. This improves the user experience by making the data easier to understand. Next, we generate smart weather-based recommendations. Based on factors like rain probability, temperature, humidity, and pressure trends, we provide useful suggestions to the user. For example, if there's a high chance of rain, we recommend carrying an umbrella. We also detect patterns like sudden pressure drops, which can indicate storms. This makes the application more interactive and practical, not just informative. This is where we turn predictions into real-world value for the user. Finally, we have our main view function, which connects the entire system. When a user enters a city, we first fetch the current weather data. Then we retrieve recent history and forecast data, which is essential for accurate predictions. Next, we either load a cached model or train a new one if needed. After that, we process the forecast data to display the next few hours in the UI. Then we use our trained model to predict the probability of rain based on real data and trends. We also generate smart recommendations for the user. Finally, we combine all this information into a context dictionary and pass it to the front-end template for rendering. This function brings together data collection, machine learning, and user interface, completing the entire AI pipeline. All right, now that our backend is complete, let's move on to building a clean and visually appealing user interface. Inside our forecast app, we first create a templates folder, and inside it, a file called weather.html. This will contain the main structure of our application. Next, we create a static folder to manage our styling and JavaScript files. Inside static, we organize everything into two folders, CSS and JS. In the CSS folder, we create a styles.css file, and in the JS folder, we create a chartsetup.js file. Django automatically handles static files, so we don't need any extra configuration here. This structure keeps our project clean, organized, and easy to scale. Now, let's build the main user interface using our weather.html template. We start with a basic HTML structure and use Django's template system to dynamically insert data. At the top, We load static files and link our CSS and icons. Inside the main section, we dynamically assign a class based on the current weather condition. This allows us to change the background visually depending on whether it's clear, cloudy, or rainy. Next, we divide the layout into two sections, a sidebar and a main content area. In the sidebar, we create a search form where users can enter a city. We also display current weather information like temperature, description, and location. One of the key features here is the AI rain prediction circle. We use SVG to visually represent the rain probability, which is dynamically controlled using Django variables. This makes the prediction more interactive instead of just showing numbers. On the main side, we display detailed weather statistics like wind, humidity, pressure, and visibility using a grid layout. We also show sunrise and sunset information along with total daylight hours. Below that, we display a 5-hour forecast using dynamic values passed from the backend. Then, we integrate a Chart.js graph to visualize temperature trends over time. This helps users understand patterns instead of just reading data. We also include AI-generated recommendations based on weather conditions, making the app more practical and user-friendly. Finally, we pass Django variables directly into JavaScript to render the chart with smooth gradients and animations. This makes the interface not just functional, but also visually engaging and interactive. Now, let's style our application and bring everything to life. Open the styles.css file. First, we import the Poppins font from Google Fonts to give our UI a clean and modern look. Next, we center the entire application on the screen using Flexbox. We use Display Flex, Align Items Center, and Justify Content Center to perfectly position our layout. Now, one of the most powerful visual features, a dynamic backgrounds. We define different classes like clear, clouds, and rain, and assign different background images to each. Since our HTML dynamically sets the class based on weather conditions, the background automatically changes in real time. Now let's talk about the design style. We apply a glassmorphism effect to our containers like side container and stat card. We use a semi-transparent background with RGBA Combine it with backdrop filter blur, and add soft shadows. This creates a frosted glass effect that looks modern and professional. Next, we style our AI rain prediction circle. We use SVG styling and control the stroke dash array property to visually represent the rain percentage. We also rotate the circle by -90 degrees so that it fills from the top smoothly. This creates a clean, animated progress effect. Overall, this styling transforms our application from a basic layout into a modern, production-level interface. Now, let's see everything in action. Go to the terminal and run. Python manage.py run server. Open the browser, and here's our complete AI-powered weather forecasting system. Let's test it with a real city and, for example, Paris. As soon as we search, the system fetches real-time data, collects the last 24 hours of historical data, and loads or trains the machine learning model. It then processes all the features and generates a prediction. Look at the AI rain probability circle. This is based on real pressure trends and historical patterns. Below that, we have a dynamic temperature graph showing future trends. We also have detailed weather stats and smart recommendations based on current conditions. All of this is powered by real data and a trained machine learning model. This is not just a weather app, this is a complete AI-powered system. This is how you can build a production-level machine learning application from scratch. If you found this helpful, make sure to like the video and subscribe to the channel for more AI and machine learning projects. Let me know in the comments if you want me to expand this further. Thanks for watching, and I'll see you in the next one.